Today's paper is Closing the Loop, Universal Repository Representation with RPG-Encoder by Jane Luo, Chengyi Yin, Xin Zhang, and their colleagues.
Yeah, this one's a heavy hitter for anyone working on autonomous software agents.
So here's the 60-second summary. The core problem, really, is that existing agents have this reasoning disconnect. They look at API documentation, which gives you semantics, but no real navigation.
Or they look at dependency graphs, which give you structure, but almost no intent.
It's the classic dictionary versus map problem.
Exactly. You know what the words mean, or you know where the roads go, but you never get both at the same time.
And the solution they propose is the RPG-Encoder. It basically generalizes the repository planning graph into one unified representation, and it treats repository comprehension and generation as inverse processes.
Right, using semantic lifting to get the code into the graph.
Yeah.
And incremental evolution to handle commits.
And that incremental part is just huge. It reduces the maintenance cost by 95.7%. The results. It gets state-of-the-art on SWE-bench verified. We're talking 93.7% accuracy at 5 with Claude 4.5. And maybe the most shocking number, it hits 98.5% coverage on RepoCraft for Reconstruction.
Which means it's actually, finally, closing the loop between a high-level idea and the low-level code.
Welcome to AI Paper Podcasts. I'm your host.
And I'm your expert co-host.
So today we are dissecting this RPG-Encoder paper because, frankly, the numbers on SWE-bench are getting to a point where you just have to pay attention.
You really do.
But before we even get to the benchmarks, I want to drill down into this reasoning disconnect idea. The authors frame this as the fundamental blocker for AI in software engineering.
It absolutely is. If you've ever built a RAG pipeline for code or, tried to get an agent to fix a bug in a repo it's never seen before, you've hit this exact wall.
The wall being just navigation.
Navigation and context, yeah. Think about the current landscape. You've got, two main ways to show a code base to an LLM. Option one is API documentation.
Which is great for semantic intent. It tells you what something does.
Right. It tells you what process payment does. The arguments, the return values.
Yeah.
It's the definition.
Yeah.
But it's totally unstructured. It's just a big bag of documents. It has no global navigability.
So the agent knows what the function does, but it has zero clue where that function actually sits in the overall architecture or who calls it.
Precisely. It's like having a dictionary for a language you don't speak. You can look up the words one by one, but you can't form a sentence.
Okay, so what's option two?
Option two is the dependency graph. This gives you the structural logic.
The subway map, this thing calls that thing.
Correct. It's very execution-centric, but it completely lacks the why. You can see that module X imports module Y, but you have no idea if that's like a critical data dependency or just some logging utility it's pulling in.
So the disconnect is that agents are stuck. They're trying to map this high-level intent like fix the login bug to the low-level code, but they're looking at these totally fragmented, incomplete pictures.
Exactly. And the authors made this really interesting point. It's almost philosophical, but it's super practical. They argue that repository comprehension and repository generation they're actually inverse pathways of the same reasoning cycle.
Okay, explain that. Inverse pathways.
So think about how you write code. That's generation. You start with a sparse, high-level intent. I need a user authentication system.
Right.
Then you expand that intent into this really detailed, noisy implementation classes, error handling, all the syntax.
Okay, so generation is basically an expansion of an idea into code.
Right. And comprehension is the exact reverse. You take that noisy, verbose implementation, all that code, and you need to compress it back into that high-level intent. You need to be able to look at it and say, oh, right, this whole pile of code is the auth system.
And most tools we have now can only do one or the other. They can't go both ways.
That's the key. The RPG-Encoder is designed to be this unified representation that supports both directions. It's the bridge between the two.
So let's talk about how they build this bridge. The whole methodology is based on this repository planning graph, or RPG. Now, I know RPGs have been around for a while as blueprints for writing code, but using them for reading code is the new part, isn't it?
That's the big innovation here, yeah. They are basically reverse engineering the blueprint from the finished building. And to do that, they use a process they call semantic lifting.
Semantic lifting. It sounds like something out of a sci-fi novel.
A little bit, yeah. It's a multi-stage encoding process. It starts with the raw code. The system parses out what it calls low-level nodes, so your functions and your classes.
Okay.
And from those, it extracts two things: functional descriptions, which is the semantics, and code metadata, which is the structure.
So far, that sounds a lot like standard static analysis.
It is at first, but the magic really happens in the next step, which they call hierarchical aggregation. The system doesn't just leave you with a flat list of 1,000 functions. It starts to cluster these low-level nodes into what it calls functional centroids.
Functional centroids. Okay, break that down for us.
Imagine you're looking at a folder with 50 different Python scripts. A centroid is like an emergent category. The system realizes, hey, these 10 functions all seem to deal with string formatting, so it groups them. Then these 5 functions are all database connectors, so they get their own group.
So it's dynamically creating a logical directory structure, not one based on file paths.
Exactly. It builds out a whole hierarchy. And the graph you get at the end is what they call dual view. The edges represent 2 things at once. The hierarchy, so parent-child relationships, and the static dependencies, the caller-callee relationships.
That seems incredibly powerful. You get the zoom-out view of the centroids, but you can still follow the zoom-in wires of the dependencies.
Yeah.
But yeah, to play devil's advocate here.
Go for it.
Graph approaches usually die for one big reason: maintenance.
The stale graph problem, yes.
Right. I mean, if I have a massive repo, 1 million lines of code, and I change one tiny utility function that's used in 500 different files, do I have to rebuild this entire fancy graph from scratch? Because if I do, the token cost is just going to bankrupt me.
And that is exactly why previous attempts like this have failed. But this is where the authors introduce incremental evolution.
This is their update mechanism.
It is. Because the graph is structured hierarchically, they don't have to reparse the whole repository. They just parse the commit diffs.
Just the changes.
Just the additions, deletions, modifications. They trace which nodes are affected by that change, and they update only that tiny subgraph. The efficiency gain it's honestly staggering.
I'm looking at the chart right here. For a standard large repository, a full rebuild of the graph takes about 14.7 million tokens.
Which is hefty. That is not something you want to be running on every single commit.
Not at all. But the incremental update, it's just 633,000 tokens.
That's a 95.7% reduction in overhead.
That completely changes the calculus. It means the cost of keeping your documentation up to date is totally decoupled from the size of your code base.
Exactly. Your repo can grow to 10 gigabytes, but if your pull request is small, your update cost is small. It makes this idea of real-time documentation actually feasible for the first time.
Okay, so we've got this graph. It's semantically rich, it's structurally accurate, and it's cheap to update. Now we need to put an agent in the driver's seat. How does an LLM actually navigate this thing? It's not just reading a text file anymore.
No, it's not. The RPG acts as a structure-aware interface. And the paper outlines 3 specific tools they give the agent to use.
Tool use, it's all the rage right now. What are they?
So first is search node. This is your standard keyword retrieval. Find me login, find me credit card.
Standard RIG stuff.
Pretty much. Then there's fetch node. This lets the agent pull the full details of a specific node it's already identified. But the real game changer is a third one, explore RPG.
Explore RPG, that sounds like an open world game command.
It kind of is. It lets the agent traverse the topology. It can move up to a parent centroid to get broader context or down to the children nodes, or it can move sideways across dependency edges to see what calls what.
And did they see any specific behaviors emerge when the agents use this?
Oh, yeah. They analyzed the trajectories of strong models like Claude 4.5, and they found a very clear pattern they called search then zoom.
Which is, that's exactly what a good senior engineer does, right?
It is. The agent starts with Explore RPG to get a high-level map of the functional centroids. It figures out, okay, the bug is probably in the data processing area, not the UI area, and only then does it zoom in.
Contrast that with what usually happens with these agents.
Well, weaker models, or agents without this graph, they just flail around, they search a keyword, get 50 results back, try to read all of them, run out of their context window, and then just hallucinate a fix.
So Explore RPG lets the model filter out all the noise before it burns its context window.
That's it. It uses the structure to prune the search space.
Let's get into the evidence. You mentioned SWE-bench verified. For those listening who aren't glued to the leaderboards, this is pretty much the gold standard for testing software engineering agents.
It is. It's a data set of real-world GitHub issues, bugs, feature requests. The agent actually has to solve them.
And the RPG-Encoder with Claude 4.5 Sonnet, it hit 93.7% accuracy at 5.
And to put that in perspective, it beats other strong baselines like Orcaloca by over 14 percentage points.
That is a massive gap in this field. We're usually fighting for, what, 1 or 2%? Why did something like OrcaLoca fall so far behind?
It came down to precision. The ablation study showed that OrcaLoca had decent recall. It could find some of the relevant files, but its precision was way lower. It was just retrieving too much irrelevant context.
It was getting distracted by shiny objects.
Basically, by coupling the semantic features with the topology of the graph, RPG saw a 6.9% jump in precision and a 10.7% jump in recall. It just stops the agent from going down these rabbit holes that look semantically similar, but are structurally completely unrelated.
Okay, but there was another benchmark that I think is actually more revolutionary, even if it's less famous than SWE-bench. And that's RepoCraft.
Oh, RepoCraft is fascinating. This wasn't about fixing a bug. This was a repository reconstruction task.
Explain that to the listeners. What were they actually asking the AI to do?
They took a complex, real-world, library-like scikit-learn, or the requests library, and they fed the agent only the RPG representation. No source code at all, just the graph. And the prompt was basically rebuild the entire code base from this.
Here is the map, now build the city.
Exactly. And to benchmark it, they compared it against agents that were given the official API documentation for those libraries.
And the difference was brutal.
The agents using only the standard API docs, they recovered about 17% of the original code volume.
17%. That's a failing grade. That's an F-.
It just proves that documentation is passive. You know, they list definitions, but it doesn't contain the blueprint. It doesn't tell you how the components interact or the logic of the architecture.
And the RPG-Encoder.
98.5% coverage with GPT-5 Mini.
Wait, 98.5%? That's almost lossless?
It's practically lossless. And crucially, the code it generated had an 86.0% pass rate on the original unit tests.
That's wild. That implies the RPG graph somehow captures the soul of the software. It holds enough information to fully instantiate the logic.
The term that comes to mind for me is digital DNA. If you have the RPG, you can clone the organism. This is what validates their claim that this is a universal repository representation. It's not just a summary. It's a compressed, high-fidelity encoding of the code's real intent and structure.
I want to pause on the implications of that for a second. If you have a representation that's this accurate, this complete, it opens up doors for things like automatic code migration.
Absolutely. Think about all those legacy systems out there. COBOL mainframes.
The nightmare of every bank on the planet.
Right. If you can parse that legacy code into an RPG, you suddenly have a navigable map. You can ask questions about its intent. And because of this reconstruction capability, you could theoretically ask a model to reconstruct that entire repository in, say, Python or Rust.
While preserving the exact structural logic of the original.
Exactly. You're not just translating syntax line by line anymore. You're translating the whole architecture.
But before we get too carried away, let's do our due diligence. What breaks it? They did ablation studies. What are the load-bearing components here?
They tested removing two main things: the semantic features and the dependency edges. When they removed the semantic feature, so taking away the what does this do descriptions, the agents basically went blind.
Cost goes up, success goes down.
Way down. They just evolved into trial and error. But when they removed the dependency edges, the structure, the token cost, just exploded.
Because without the edges, the agent has to read everything to find the connections.
Exactly. It just confirms that you need both the map and the legend to navigate.
And even with the full system, they didn't hit 100%. They hit 93%. What happened in that last 7%? Where did it fail?
So the single largest failure category, almost half of all the errors, was still search and exploration.
Even with the Explore RPG tool?
Even with the tool, yes. The paper calls it granularity mismatch, or evidence misread.
Can you give me an example of that?
So an agent might successfully navigate to the right functional centroid, say the payment processing cluster, but then it just stops looking. It assumes it has enough information, but the actual bug is buried 3 layers deeper in some obscure helper function.
So it's the I know what neighborhood I'm in, so I'll stop asking for directions problem.
Exactly. Or it misinterprets a function description. It reads validates user and thinks, okay, this checks passwords, when in reality, it only checks for a valid email format. That's a very subtle semantic error that the graph structure can't always fix on its own.
So the map is accurate, but the navigator, the LLM itself, can still make a wrong turn or misread a sign.
Precisely. The RPG solves the where am I problem, but the is this exactly the logic I need problem still relies on the raw reasoning capability of the underlying model.
Which is why we see better performance with Claude 4.5 versus weaker models. The graph empowers the model, but it doesn't replace the need for actual intelligence.
Correct. It's a force multiplier, not a replacement.
So let's wrap this up with the big picture. We have a system that unifies intent and implementation. It updates itself incrementally, so it's always fresh. And it allows an AI to understand the code well enough to rebuild it almost perfectly from scratch.
It basically solves the context window problem for large code bases. Instead of trying to stuff 100,000 lines of code into the context, you just feed it the RPG.
Yeah.
It's cleaner, it's denser, and it's structured.
It makes this whole concept of self-maintaining software feel a lot closer to reality. We always talk about self-healing code, but that usually just means, restarting a Kubernetes pod. This is much deeper.
This is structural understanding. It's giving the AI a mental model of the software that's consistent with how humans think, but it's scalable in a way that humans just can't manage.
And that leads me to a final, slightly provocative thought for everyone listening.
Let's hear it.
If we now have a representation, the RPG, that allows an AI to fully reconstruct a repository, and we have a mechanism for that AI to update that representation incrementally as the code changes, are we looking at the first real step towards software that can truly understand and refactor its own architecture in real time?
That is the trillion-dollar question, isn't it?
Not just fixing bugs, but actually evolving its own design.
If the map and the territory are perfectly in sync, the explorer can become the architect. It's a fascinating possibility.
It certainly is. For those of you who want to check out the diagrams, which I highly recommend, especially the dual view graph visualizations, the paper is Closing the Loop: Universal Repository Representation with RPG-Encoder by Jane Luo and team.
It's definitely a read worth your time if you're building agents.
Thanks for tuning in to this episode of AI Paper Podcasts. We'll catch you on the next deep dive.